30 seconds. All right, go ahead. I'm gonna wait till 30 seconds.
You got some sort of exciting. Okay, good. That's the nature of it. We have a bit of a breather now in terms of what's going on in 61B. We haven't finished one of these yet. Didn't finish it. But other than that, we got another project coming up in a bit, but for now we're going to focus on the math. So without further ado, I'll kick it over to Justin to be mapping and I'll key it. Thanks.
All right, can people on Zoom hear me?
Also, can you enable chat?
Yeah.
Yeah.
All right, we're gonna enable chat and it is all
right. Welcome to Asymptotics Analysis 2. It is another Math 61B lesson. All right. This is kind of a CS70 preview. We won't be expecting you to do fully all the stuff that we do today, but it'll still be useful. All right, let me just. All right. So I want to start off with a bit of a warm-up. All right. So just for today's lecture, just some ground rules. Any functions that we discuss today are going to be functions in the mathematical sense. So we're not talking about programs, which are things which have instructions that you apply like one line at a time. We're talking about mathematical functions, which are more similar to the sense of like a dictionary. You put in one input, you get out an output. You don't really care about how you get the output. It's just a mapping from inputs to outputs. And we'll further look mostly at real valued strictly increasing functions. So these are functions that take in as input in a number, let's say 1, 2, 3, and output some other number, 149 maybe. In most contexts, we'll be dealing with strictly increasing ones because the larger the input is, the more time it takes to run on it. We won't be asking you to do much math beyond this lecture. 61B isn't a math class, but for today only, we'll be kind of delving really deeply into the mathematical rigor and making sure we fully understand what's going on. You won't need to create these kinds of proofs on exams, for example, but this type of thinking might help out a lot with those harder exam questions. All right. Any questions on ground rules before we get moving? All right. So yeah, not all of this is fully within something you're expecting to do, but it's useful to think about. So let's start off with just a quick thought experiment. This is kind of referencing this idea or this story about the guy who invented chess. Am I getting feedback loop? I think I'm about to get a feedback loop. All right. So the king offers the inventor of chess these two options. The first one is $1 million a day, every day for the next 64 days. The second option is 1 grain of rice on day 1, 2 grains on day 2, 4 grains on day 3, doubling every day until day 60. And just as a quick show of hands, how many people prefer option 1? $1 million a day for 64 days? Seems good. How many people prefer option 2? 1 grain of rice on day 1, 2 on day 2? All right. Why do you want those? Try and discuss with your neighbors to see if you can come to some consensus. I think let's come back at 114. All right. Let's bring everyone back. All right. Now that you've had a chance to discuss, has anyone changed their opinion? Anyone want one versus two? Yeah.
Yeah, I said I want one burger instead of two.
All right. You say you want one instead of two? Why?
Because I know the two is the exponential growth, but it's rise and it's not a conventional thing.
Yeah. Two is the exponential growth, but it is rice. How valuable can rice be? Yeah. Yeah. It's a lot of rice. Yeah. Huh? You can solve world hunger with two. But having that much rice would push the right. All right. This is an interesting question. Let's figure it out. All right. So let's do some mathematical analysis to see how this behaves. First off, let's just look at how much money you get on option one. $1 million every day for 64 days. How much money do you get at the end? $64 million. All right. How much would you say one grain of rice is worth? Half of a cent? Well, I would use some Fermi estimations. I'd estimate that, let's say, a rice grain is worth 1/100th of 1 cent. All right. So on day one, we get 1/100th of a cent. Day two, we get 2/100th of a cent. By day 10, we're getting up to about 10 cents a day. By day 20, we're about $104. Day 34, we are already at $1,717,000. Around day 50, we hit approximately the entirety of all rice crops that are produced on Earth each year, which means that everyone else on the planet is now going hungry. We failed to solve world hunger with that, sorry. And by day 64, we are at about $1.8 quadrillion, which is just about the total economic value of everything that has been made by humans in all of history. It would push the price of rice down. On the other hand, it's a scarce resource. In any case, option two is going to make you way, way, way more. It's way more valuable than option one. The story, depending on who tells it, either goes that the person who chose option two gets beheaded by the king because he was too greedy, or the king laughs and gives him option one anyway. Or the king doesn't realize that option two is that much that good and pays until around day 30, at which point he gives up. But in any case, let me ask you another question. Instead of being $1 million in one grain of rice, what if we just changed those values a bit? Let's say that instead option one is X dollars a day for the next Z days, where Z is just some arbitrary number, X is some number, and Y is some really small amount. On day one, you get just Y dollars. Day two, you get 2 times that. Day three, you get 2 times the previous day, and so on until day Z. And my question is this: does option two always eventually become better? So regardless of how much X is, if X is a Google dollars and Y is 1/octillionth of a penny, is it still true that eventually option two becomes better than option one? And try and discuss this, find a logical argument as to why that's true. Let's take a minute or so for this. All right, let's bring everyone back. So just as an immediate preview, how many people say yes, eventually option 2 will become better than option 1? How many people say no? Depending on the values of x and y, there's a chance that option 2 always stays worse than option 1. All right, for the why would you say that? Yeah.
Why could he, oh wait, I misunderstood. Never mind.
Okay. Yeah, if y is 0, then yes, option 2 would not work, but yeah.
So like option 2 is kind of like a geometric sequence where you can have that kind of formula. So basically you have an Rn in it, which is the most important part. And R1, it's always like XZ. So if you use the option 2's summation formula divided by option 1, you will still get a exponential number that you know is greater than 1. And then that means option 2 should be greater.
Yeah. There's a lot of like math that you said. You are actually preempting quite a few things that I'm going to be discussing, but the overall logic is correct. In effect, option 2 grows every single day. And eventually, after enough days pass, option 2 is going to be giving you more money than option 1. Right? Option 1 is just a fixed amount every day. Option 1 just keeps growing and it doubles every day. So it's going to get really big really quickly. Eventually, option 2 is going to be bigger than option 1. And after enough days where option 2 is beating option 1, you're going to have more money coming from option 2. So eventually, option 2 wins, regardless of what values y and x are. Now, if you think about it from a 61A perspective, 61A discussed kind of orders of growth in kind of these nebular manners. We said that option 1 would grow linearly, option 2 grows exponentially, and eventually anything exponential will always grow larger than anything linear. Now we need to define what we mean by this. Eventually the exponential function will always grow larger. And that's kind of going to be what we're discussing today. Intuitively, we want to be able to define linear and exponential in math terms so that an exponential function is greater than a linear function, in the sense that eventually it's going to grow bigger than a linear function, no matter what you start with. So we finished off last lecture by discussing the actual notation we'll be using. And I thought it'd be useful to kind of just briefly review that. So we defined this method as our theta notation. And the way we define theta notation is that a function r of n is defined to be theta of f of n if there exists constants x or k1 and k2, such that k1 times f of n is less than or equal to r of n is less than or equal to k2 times f of n for anything greater than some lower limit n0. In effect, for very large n, the value of r of n gets kind of squeezed in between constant multiples of f of n. So as an example, 4n squared plus n, that gets squeezed between two functions that grow as the size of n squared. We can say, for example, r of n is 4n squared plus n, and f of n is the n squared function. The constants that we use, k2 and k1, you can choose a lot of them, but the ones that I'll pick here are k1 is 3 and k2 is 5. In effect, we're saying that 3n squared is going to be less than 4n squared plus n, and 5n squared is going to be greater than 4n squared plus n. So that means that r of n kind of grows at about the same pace as f of n, up to a constant factor. Any questions on this? All right, let's get into a few exercises on how we can use this. We're not going to be doing the math quite yet, but I just kind of want to get a sense of what you intuitively think the theta bound is for each of these. So what would you say the theta bound for n cubed plus 3n to the fourth is? Theta n to the fourth, I heard an n squared over here. Yeah. How many people say n to the fourth? How many people say something else? Okay. Can you explain why you said n squared?
Because it's n raised to 4, so we are looking at like if you were to map it out as an arithmetic sequence, you'd realize that eventually it takes the form of a quadratic, much less n squares.
Okay, so you're saying that eventually it takes the form of an arithmetic sequence?
Yeah, I mean, you map it out as an arithmetic sequence, and then if you were to eventually the order of growth would be.
Okay. There's one slight issue with that. It's that arithmetic sequences are specifically linear. They grow linearly. There's a fixed difference between each step.
Oh, sorry, the geometric.
It's not geometric either. Geometric is a fixed ratio between items. This is actually just neither of them. It's a quartic sequence if you want to like be specific, but we don't necessarily have names for all of them. Yeah. Interesting idea though. Yeah, you are correct that if it was an arithmetic sequence, then it would be quadratic. Yeah. I would say it's n fourth too. We don't have yet a way to prove that, but I would say that that seems like a reasonable assumption. What about the second one? 1 over n plus n cubed? N cubed? Yeah. What about 1 over n plus 5? All right, I'm hearing some 1 over n's, I'm hearing some 1s, and I'm hearing some 5s. Some people are saying 1. All right, which one grows faster, 1 over n or 5? How many people say 1 over n grow faster? How many people say 5 grow faster? Why would you say 5 grows faster? Yeah, because 1 over n shrinks. It's negative growth.
Yeah.
It's going backwards. So yeah, I would say it is theta of 1. Theta of 5 is also correct because it is still theta of 5. It's just 1 is considered more of the canonical item within that class. We kind of pick one item that represents the entire class, and for the constant bound, we always pick theta 1. All right, what about n e to the n plus n? N times e to the n? Yeah. And then for this 40 sine n plus 4n squared, what would you say? N squared. Yeah. Intuitively, we're kind of just taking the largest thing, the thing that grows the fastest, and then picking that as our order of growth, getting rid of any constants at the start or coefficients. So in big theta notation, these are true statements. You will be writing these as 1 over n plus n cubed is contained within the theta n cubed family. In effect, theta n cubed denotes all functions that grow as fast as n cubed. And we're saying that this 1 over n plus n cubed is one item within that. This E symbol is the notation for symbol or a set contains. So this thing here, theta f of n, is a set of functions. And we're saying that R of n is contained within that set, is an element of the set. So let's do an example of actually doing the math. R of n is 4n squared plus 3n times the natural logarithm of n divided by 2. Just quickly, what do you believe the order of growth is? N squared. So we believe that f of n should be n squared. But let's actually prove that that's true. Let's find values of k1, k2, such that this is true. Such that n squared times k1 is always less than this, and n squared times k2 is always greater than this, with the possible exception of small values of n. Let's give a minute for that to discuss.
We have to establish okay. No, it's not. Oh, Q&A, really, that's square. All right. I only watch it. Yeah, but I guess I do. I just really you look at the graphs of all the we start off with log. Is it log? But in general, I guess we're
All right, let's bring everyone back together. So, all right. So you can definitely pick a lot of different values for K1 and K2. Pretty much any value you find will work for at least one of these. But what do people say for K1 first? Any suggestion for K1? Yeah. 4? I think 4 might be a bit big on this one. Well, I think 3 is actually going to be bigger than R of n. Keep in mind that we have a division by 2 at the very end. So this ends up being like 2n squared plus something small. I'd personally say that anything less than 2 would count for K1. Anything greater than 2 will count for K2 eventually. But let's kind of show that that's true. I picked 1 and 3 for this case. You could have picked any other numbers. As long as K1 and K2 are positive numbers, it's perfectly fine. I could have picked K equals 0.00001 if I wanted to. Now, how do I show this? Well, one way is I could just graph it. That's 3x squared, that's x squared. Those are in blue and green respectively. And the red line is the 4x squared plus 3x natural log x divided by 2. Looks like it's staying within the bounds. Are you satisfied with this proof?
not the tightest bound.
Huh? It's not the tightest bound. I'm not fully satisfied with this though. Because if I take a look at this, right? I claimed that 1.9 and I claimed that anything less than 2 is going to be fine and anything greater than 2 is going to be fine for this. So what if I do 1.9 and 2.1? Now all of a sudden, the red line is outside the bounds between the blue and green. Do you think that 2.1 is not a good bound, that we should have picked a bigger number? Eventually, it is going to be bigger. In fact, if I keep scrolling up, the blue line gets closer and closer to red, and then it bypasses it, finally. After it goes far enough up this slope, eventually the red line goes between the blue and green, so the theta bound still holds. We only care for sufficiently big numbers, so we don't care that the red line ends up staying outside these bounds for small values of n. As long as eventually it makes it there, we consider these bounds to be correct. So the problem is, if it's possible for the red line to go between the blue and green this way after a long time, then what's stopping this 3 and 1 bound? What's stopping this 3 and 1 bound from not working somewhere really, really far down the line? I don't know. So sometimes you need to do kind of full algebra. Here's how I might do the algebra. You don't need to do this officially in every single time, but it's useful to kind of get a sense of how this might work if you wanted to formally prove this. So let's say that R of n is this function, 4n squared plus 3n ln n divided by 2. And what I'm going to do is I'm going to show these inequalities one step at a time. First, I'm going to show the lower bound, and then I'm going to show the upper bound. So first off, I'm going to say that this number is just 2n squared plus 3 over 2n times ln n. Are people okay with that? Do we agree that this is true? Yeah, it's just distributing the two. We're doing algebraic manipulations. And the second thing I'm going to say is this is going to be strictly greater than just 2n squared, because 3 over 2 times n log n is something bigger than 0. If I subtract that part, then I'm getting a smaller value. And 2n squared is always greater than or equal to n squared. Are we agreeing with that? So if this is true, then n squared is less than or equal to this. So that means we fulfilled this side of the condition. F of n, where f is n squared, is always less than or equal to r of n. And k1 is just the number 1 in this case. What about on the other side? Well, this thing is still 2n squared plus 3n over 2n times ln n. If 3 over 2 ln n is less than n, then I will say that 3 over 2n times ln n is less than n squared. Why is that? Because we're just multiplying n on both sides. Do we agree with this statement? As it turns out, 3 over 2 times natural log of n is less than n for all values of n. Here's kind of another graph that shows this. It's not a foolproof, but we can see that the natural logarithm gets less and less steep as we go along, whereas the x just stays steep. So it seems reasonable to say that no matter how far along the line we go, 3 over 2 natural log n is always going to be less than the value of n. If you want to be more formal, you would have to prove this is true, but that's beyond the scope of this class. But once we have that, that means that 3 over 2 n log n is less than n squared. So that means 2n squared plus 3 over 2 n log n is less than 2n squared plus n squared. We're just replacing this thing with something that's bigger. 2n squared plus n squared is what? 3n squared, which means that this statement is true. 2n squared plus 3 over 2n log n is less than or equal to 3n squared. Which means we have shown that r of n is less than or equal to 3 times f of n. Putting it together, f of n is less than or equal to r of n is less than or equal to 3 f of n for all n greater than 0. So we have found constants k1, k2, and n naught that fulfill these conditions, and we can claim that r of n is in theta of n squared. All right. That was a lot of math. That was a lot of algebra. We went into a lot more detail than you would need to. It's mostly just showing that regardless of how you try to argue against me, you don't have a way to say, no, your statement isn't true. I kind of like to think about proofs as like winning an argument with someone who is absolutely going to try and tear apart your argument as best as possible. Now, the formal definition here, it's not going to change anything about determining your order of growth. Your intuition is generally going to be correct. The math is just there to kind of officially prove that that's true. But it's still useful to know these definitions for those weird cases where the intuition isn't quite correct. Sometimes when you do the math, you realize that something you thought was a theta bound is actually not, and there's something slightly different. So you do need to know these formal definitions. But in most cases, you can kind of just assume that it's going to work fine. You just got to be a bit careful with that. All right, any questions up to here? All right. Now, we use big theta to describe this order of growth. We will eventually be using big theta to describe the rate of growth of the runtime of a piece of code. That's going to be kind of our topic for next Monday. We'll come back into looking at runtime of functions or programs. Sorry. But as it turns out, theta bounds aren't always the most convenient. Whereas big theta is informally thought of as something like equals. So something 3n fourth plus n cubed is approximately equal to n fourth. So we say it's theta n fourth. We have two other symbols for when we can't get an equality, but we can get less than or greater than, kind of an upper bound and a lower bound. So big O can be thought of as less than or equal to, and big omega can be thought of as greater than or equal to. Here are some examples of true statements. For example, n cubed plus 3n to the fourth. That's theta of n to the fourth. because it's equal to n to the fourth, but it's O of n to the sixth because it's less than n to the sixth. And anything bigger than n to the fourth, it's O of that. This is a really, really big function, n to the power of n factorial. That's going to be O of most things you see in this class. Not all things, but most things. Because it just grows way, 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 way faster than anything you could get with polynomials. On the other side, omega bounds are kind of the lower bound of things. So n cubed plus 3n to the fourth, it's going to grow faster than omega of 1. Omega of 1 says it's not growing at all, and n to the fourth is going to grow. The formal definitions are here. In effect, here's the theta definition, right? We said that we need to have the lower bound, k1 times f of n, and k2 times f of n forming the upper bound. The O bound is just this. We get rid of the k1 times f of n, so we don't have the lower bound anymore. We're just checking to make sure that it's upper bounded by this O side. And the omega bound definition is the exact opposite. We just remove the right side and we get the left side only. Now we'll see why these are useful in the upcoming disjoint sets lectures. We often use O and omega when we can't get a theta bound because computing the theta bound is too hard for us. But we generally do prefer a theta bound if it is ever possible to actually get that. Similarly, we prefer saying O bounds that are as small as possible and omega bounds that are as big as possible because those give us more information. We could, in theory, say that anything is omega 1, but that doesn't really help us explain anything because everything is omega 1. Similarly, we could say everything is O of n times n to the n factorial to the power of Graham's number. But that's not particularly useful because pretty much everything is. You're not describing something too much. Here are some examples of elements within each family. So theta n squared contains the functions n squared over 2, 2n squared plus 38n plus n. All these functions are also in O of n squared and omega of n squared, but the O of n squared has a few other things like the natural log of n. The omegas have bigger things like n to the n factorial. You can kind of see how these families behave. And we're always saying that any function is contained within some of these theta bounds, some of these O bounds, some of these omega bounds. All right. Now, let's try and prove a few things about these theta bounds. I like to use these definitions in actual proofs to get a better sense of how they work. So in lecture 11, we assumed a few things. We assumed specifically that when dealing with order of growth, the largest term dominates. So we were saying like we can ignore the n cubed term when there's an n to the fourth term. We didn't actually prove that yet. And we also didn't prove that polynomials with higher exponent dominate over polynomials with lower exponents, that the n to the fourth is actually going to grow faster than the n cubed. Let's try and actually prove some of these statements. So here's just the definitions again. I just rewrote them here so that you have them available. And let's try and figure out some proofs. As an example, if something is O of g of x and something is omega of the same thing, then it is going to be theta of the thing. Do we agree with the statement? If something is greater than or equal to g of x and something is less than or equal to g of x, then it should be equal to g of x. Yeah. How many people agree that the statement should be true? Feels like it's true. Let's actually try to prove that this is actually the case. When we say that f of x is O of g of x, all we're saying is that this is true. We find there exists some b and some n naught, such that f of x is less than b times g of x for anything greater than n naught. So for sufficiently large values of n, this inequality holds true. The omega is the same thing, only we say that the lower bound is also true for sufficient values of n. Now, we do have to be a bit careful here because n naught and n prime naught might be two different values. But we can just take the max of these two. And at the max of these two, then both of these inequalities will hold. Now, if both of these inequalities hold, then by the definition of theta bound, f of x must be theta of g of x. So this kind of shows us that if f of x is both O of g of x and omega of g of x, then it must be theta of g of x. And we'll be using that often when proving a theta bound. on more complicated things, because it's often easier to show that something is O of a function and something is omega of something than it is to show that it's theta of something just directly. Let's try out an example. This is kind of that same statement that the lower order terms don't matter. In effect, if g of x is O of f of x, so g of x is less than or equal to the f of x, then the f of x plus g of x is going to be theta of f of x. The g of x effectively doesn't matter and can be safely ignored. Let's take a few minutes, 2 minutes or so, to discuss with your neighbor to try and see if you can prove this is true. As a reminder, we're going to be trying to find both of these inequalities for the f of x for theta bound.
Yeah, no, I.
Yeah. All right. Did I turn off the mic? I turned off the mic.
That's.
All right. Let's bring everyone back. Final thoughts. All right. How did people do on this? Feeling good-ish? Iffy? Had no idea? I see. Kind of a mixed bag. Well, let's try and go one step at a time. In order to prove a theta bound, we want to prove two of these inequalities. First, that f of x is less than or equal to b times g of x, and second, that f of x is greater than a times g of x for some constants a and b. So, did anyone have a way to show that f of x plus g of x is O of f of x? That f of x plus g of x is always going to be less than or equal to f of x? All right. No worries. How about the other direction? Can we show that f of x plus g of x is always going to be greater? Oh, yeah.
For life, then, you could say that g of x is always going to be less than f of x. So f of x plus g of x is less than 2 of f of x. And f of x is going to be lower than f of x. So.
Yeah, that's a good way to explain it. In effect, g of x is going to be less than f of x. It's not quite less than f of x. It's less than b times f of x, some constant times f of x. So if you just add f of x to that, that's just b plus 1 times f of x. So f of x plus g of x is going to be less than or equal to b plus 1 times f of x. And that gets you that bound. Do you have something? I think I understood what you're saying, kind of. I couldn't quite hear all of it, but I think it sounds right. Yeah. How about on the other side? Can we show that f of x is f x plus g of x is always going to be greater than f of x? Yeah, as long as g of x isn't negative, you're adding f of x to something that's positive, you're going to get something bigger. So yeah, here's kind of how I would say it. For all n greater than n naught, 0 is less than or equal to g of x is less than or equal to b times f of x. This is just from the definition of the O bound and from the fact that we said g was positive. And if we just add f of x to all of these sides, we get f of x is less than or equal to fx plus g of x is less than or equal to fx plus b times f of x, which after simplification is just the exact same as the theta bound definition with a equal to 1 and b equal to b plus 1. Yeah. Overall, this ends up showing that these lower order terms won't affect things. We don't need to do this level of math anymore. We have finished all this math. We've done it once. We can now say if we have two terms and one of them is smaller than the other, we can just ignore that smaller term whenever we're dealing with asymptotic analysis. Because we've already proven that it works this way. All right. So we have other properties of O and theta bounds. We'll have a few more of these examples in discussion so you can work with them. But let's kind of look at what things you might see in actual runtime analysis. Here are some common theta classes that you'll see in this class. The first set is polynomials. So these are things like your theta 1, your theta n, your theta n squared. I count theta square root n as also a polynomial because it's n to the power of 0.5. We'll also see some exponentials, hyperexponentials. These are like your theta 2 to the n, theta 3 to the n. Theta n factorial is going to be a big one. It's the factorial of n, which is 1 times 2 times 3 times 4 up to times n. Logarithms, we'll see some logs as well. If you're familiar with them, they're logs base 2, log, etc. And in effect, we say log b of n is the number of times you need to divide n by b until you reach the number 1. That's kind of just the informal definition of log b of n. But it's fairly close to what it really is. Now, I will note that for the purposes of this class, we will use log n without a base to refer to base 10. We'll use lg of n to refer to base 2, the binary logarithm. And we'll use ln, ln, to represent base e. Usually, it wouldn't matter what the base is, so we'll just use log. But if it ever does matter, we'll be using this for future classes. Most of the time, it doesn't matter, so we'll just use log. But if it does matter, we will do this. We might have some combinations of the above, like n log n, for example. And we will have other things that aren't on this list. For example, like the inverse Ackermann of n is going to show up next Wednesday. But these are the ones that you'll really have to deal with and have to do math on. The others are kind of just one-offs that we find randomly. Let's try comparing some of these classes. As we mentioned here, I think, earlier, there is another way to use this definition. If we just manipulate this theta definition a bit, just dividing by g of x, this is possible because g of x is always positive. then we get this simplified version of theta, which is that the ratio between f and g stays bounded between a and b. So if f of x is O of g of x, then that means that the f of x divided by g of x is going to be upper bounded. The ratio between the two stays below some constant. Or in the other way, the inverse ratio doesn't go below a certain value. A theta bound indicates that it's going to stay bounded within two areas. So the ratio is going to stay within two numbers. And if the ratio goes either towards 0 or goes up to infinity, then that means that the ratio, that means that you're not in the same theta class. As kind of an example, remember that function from earlier, 4x squared plus 3x ln x over 2 divided by x squared? As it turns out, if you divide that by x squared, then you get this graph that always stays really close to 2. Eventually, no matter how far you go, it'll get closer and closer to 2 as you go along. You can do some like really difficult math proofs to show that, but in effect, it ends up getting closer and closer to 2. So we say that it is theta bounded because the function stays bounded eventually. You don't have to do like the formal math on this, but I kind of want to get a sense of like what these functions are. So let's take the last few minutes of class to kind of compare some functions together. Which one do you think is bigger, x squared or x cubed? Do you think they're the same size? What about 2 to the x and 3 to the x? What about log 2x and log 3x? And let's discuss for, let's say 3 minutes here.
Like the first well, I guess I guess you can do that. Yes. Right now, on the symbol. Otherwise, it's not. Sure, better sense. Would that make it effective? Right. What is the 90 seconds?
All right, let's bring everyone back. So, what do you say? How do people compare x squared and x cubed? All right, are they the same size? X squared and x cubed, are they the same size? How many people say yes? No? All right, which one's bigger then? X cubed? Okay, that seems like a reasonable statement. How about 2 to the x and 3 to the x? Are they the same size? No. Which one's bigger? 3 to the x. How about log 2x and log 3x? Are they the same size? How many people say yes? How many people say no? All right, this seems about evenly split. Interesting. If they aren't the same size, which one's bigger? Log 2x? Yeah, because it takes more steps to divide by 2 until you get to 1 than it does to do 3. Well, let's kind of go over each one. If you compare x cubed and x squared and you divide them, then you get x, which is going to diverge to infinity. So you are correct that x squared is O of x cubed, but not theta of x cubed. In effect, x squared is less than x cubed, strictly less than. And as it turns out, you can generalize this for any exponent. The larger the exponent is, the bigger the function is, and bigger exponents are always bigger than smaller exponents. You can do something similar with 2 to the x and 3 to the x. If you take 3 to the x divided by 2 to the x, you just get 3 over 2 to the x. That goes off to infinity as well. So as long as the base is bigger, you're going to have a bigger function. But with log, they're actually the same. Now, the reason why is because of some of these log rules. So, for example, one of the rules that exists in logarithms is that the log base a of b is equal to the log cb divided by the log ca. It's the change of base formula. And if you apply this in the right way, then we can show that log 3x is just the same as log 2x divided by log 2, 3. And log 2, 3 is just some constant. It's somewhere between 1 and 2. So if log 3x is just log 2x times a constant, then what can we say? Yeah, they're just theta of each other. Can we generalize to any other numbers, not just 2 and 3? Yep. Every base, no matter what, is going to be in the same theta class as log. Because of this, we often just omit the log base entirely. So we'll be saying theta of log x a lot, just because the base doesn't matter. All right. I think we'll finish off today here. Here's just a quick overview of all the functions that you might work with, just some general ideas on how they behave. And we'll continue off from there on Monday.
So how do you want to tear down, or do you have to tear down? Okay. Okay. Yeah. I gotta run. Yeah. One question about this. Yes. Yeah. Oh, right. I will say no, I'm not gonna. I say no, I'm not really. I don't know that. It seems wild. I know. It's the one that I write. How bad is it? No, no, I don't think it's that bad. I rate it out. Yeah, I don't want that's 6 hours is very hard to get by. I'm already working when I write when I was. No, 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 no. Yeah, so minus 6 hours. I can tolerate it. Why can't the TA? I don't think I've ever had a TA so without really a problem. The TAs are want at least a lot of and it's mostly because I write it. That's correct. Because like there's a large they need to check to make sure that well all they gotta do though is check it's easy to do all they have to do is check that the list that they put for the X and the Y that they're interleaved after. I mean, maybe I'll look at how bad it really is. I'm going to assume really bad because students are they're very creative. Well, I'll look and see. But yeah, all right. If you can let us prove it, then set up. Okay, yeah, sure. When does grading start? Because I would hope help fundraise. Yeah. My personal goal is okay. Anyone's ever asked me. Well, 13 years ago. No, okay, it's all. Then I will I need to do right. More like that's it. That's part of it. Yeah. I probably can do all this stuff. Yeah. You have questions?
Yeah, I have a
question. Yeah. What's that?
Between 0 and 1. Wouldn't this be smaller to understand?
Oh yeah.
Because then ln would become negative, so 3n times the negative divided by 2.
Yeah, but it's probably still going to be less than 1. I don't know.
1 times n squared, yeah, sure. But
yeah, probably not 2 times n squared. Yeah.
Okay. So in that case, it's recommended to do something lesser than 2.
Yeah, but I mean, n greater than 1 and greater than 2, it doesn't really matter. Eventually. Yeah. That's a good point, though. Yeah, what's up?
That's not the question we're like thinking about because I'm so kind of confused with the whole class and I'm like groups.
Yeah, like the informal definitions should work fine. It's kind of just like saying that it's growing at the same pace. The formal definition is it grows faster than something that's the same pace as it, and it grows slower than something that's the same pace as it, right? Because if it grows faster than something and it grows slower than something at the same time, then it must grow equal to that thing.
Okay.
Yeah.
Because if it's less than wait.
Like if you say that this thing is heavier or is heavier or the same size as this thing, and I say this thing is heavier or the same size as this thing, right? Then they both must be equal to each other.
If you say they're both heavy or equal to each other, they have to be.
Yeah. Yeah. If x is greater than or equal to y and y is greater than or equal to x, they got to be the same.
Yeah.
Yeah. It's effectively that statement.
Okay.
Yeah. Everything else is just the mathematical like sugar behind what's going on. And I kind of want to showcase that first, but eventually we are going to retreat back to the cave. Yeah, I actually have a slide all the way at the end of this section. That's like, just go back into the cave. We'll be going back into the cave eventually.
Are we the ones in the cave or we the ones?
We're in the cave.
Oh, okay, we're the ones trapped in the cave.
We want to be trapped in the cave. Because if we're trapped in the cave, then we don't need to worry about the scary world outside. We don't need to think about the scary world outside. It's easier.
We don't really have to think much about the proofs, right?
the proofs are just the way to formalize it. It's useful to come into that mindset, especially when you go into 70. But it's okay if you're like, if they're a bit high level. This is actually like a decent chunk of 104 knowledge too, because 104 does a lot of these types of like less than or greater than proofs. Yeah.
I know, but I want to understand it because I have to take CSM like later on. So like might as well like start to understand it now.
Yeah. It's just like being very precise with what you say. Yeah. Normally the informal definitions are going to be perfectly fine. They're going to be sufficient for your cases, and they are going to be basically correct.